This video covers Part 3 of Section 1.1, Statements and Logical Connectives. We want to first look at precedence rules for the logical connectives. In algebraic expressions involving the operations of addition, subtraction, multiplication, division, and exponentiation, we have precedence rules which dictate the order in which these operations are applied. In the absence of parentheses, we apply the operations in the order exponentiation, multiplication, division, addition, and subtraction. We have similar rules of precedence for applying the logical connectives. In the absence of parentheses, the logical connectives are applied in the following order of precedence. Negation is first, conjunction second, disjunction third, the conditional fourth, and the biconditional fifth. Two logical connectives of the same type are applied from left to right. So for instance, P implies Q implies R means P implies Q quantity implies R. As in the case of algebraic expressions, we can use parentheses to override these rules. To avoid any possible misinterpretation, it's always best to include parentheses in your statement forms where appropriate, even when the meaning can be determined by the rules of precedence. For an example, we want to insert parentheses in the following statement forms to indicate the order in which the logical connectives are applied. First we have not P and Q implies R. According to the precedence rules, we apply the negation first, followed by the conjunction, followed by the conditional. So this statement form has the meaning not P and Q quantity implies R. Next we have P if and only if Q implies R. We apply the conditional first, followed by the biconditional. So this statement form has the meaning P if and only if the quantity Q implies R. And next we have P or Q implies R or S. This has two disjunctions and a conditional. Recall that when we have two connectives of the same type, we apply them from left to right. This means we apply the first disjunction first, followed by the second disjunction, followed by the conditional. So the statement form has the meaning P or Q quantity implies R or S quantity. Next, we want to look at translating from English to symbolic form. In order to determine truth values of compound statements, we must be able to translate English and mathematical sentences into symbolic form. This is sometimes complicated by the fact that we often use different words and sentence constructions in English to represent the same symbolic form. The conditional and biconditional statements in particular can take various forms in English. Here are some of the forms corresponding to the conjunction, conditional, and biconditional. For the conjunction, the following phrases in English correspond to conjunctions. First, P but Q has the symbolic form P and Q. So but represents a conjunction in English. But is usually used in place of and when the statement corresponding to Q is in some way contrary to P. For instance, it sounds more appropriate to use but instead of and in a statement like, "It's raining, but I'm still going to the beach." Next, neither P nor Q means not P and not Q, so has statement form not P and not Q as shown. So neither nor corresponds to a conjunction in and statement with both parts negated, not to an or statement. The conditional statement form P implies Q can be written in English in any of the following ways. If P then Q, P implies Q, Q if P, P only if Q, P is sufficient for Q, or in order for Q, P is sufficient, Q is necessary for P, or in order for P, Q is necessary. And finally, whenever P, then Q, or Q whenever P. The first two forms in A and B, if P, then Q, and P implies Q, are both pretty straightforward. In the form in C, Q if P, the hypothesis and conclusion have been switched, but we recognize that the hypothesis follows the word if. The form in D, P only if Q, tends to cause the most confusion, with students often thinking this statement has symbolic form Q implies P. To help remember that this is not the case, note Q implies P would be written as if Q then P, or P if Q, rather than P only if Q. The forms in E and F, P is sufficient for Q, and Q is necessary for P, also tend to cause some confusion. In the first of these, the phrase is sufficient goes with the hypothesis, while in the second, the phrase is necessary goes with the conclusion. Finally, in G, whenever P then Q, we see that we can substitute other words such as when or whenever for if. The biconditional statement P if and only if Q can be written in English in any of the following ways. P if and only if Q, P is equivalent to Q, P is necessary and sufficient for Q. For our next example, we want to look at translating statements into symbolic form. We'll start with if 7 is an odd integer, then 6 is an even integer only if 42 is an odd integer. We need to first identify the component simple statements and define statement variables. The component simple statements of this compound statement are 7 is an odd integer, 6 is an even integer, and 42 is an odd integer. So we define statement variables. P is 7 is an odd integer, Q is 6 is an even integer, and R is 42 is an odd integer. Replacing the component simple statements with the statement variables, we see that the statement has the form if P, then Q only if R. Q only if R has symbolic form Q implies R, so the complete statement has symbolic form P implies the quantity Q implies R. Next, consider the statement if 42 is an odd integer, then neither 7 is an odd integer nor 6 is an even integer. This statement has the same component simple statements as in Part A, so we may use the same statement variables. We can write the compound statement in the form if R, then neither P nor Q. Since neither P nor Q means not P and not Q, which has symbolic form not P and not Q as shown, then the complete statement has symbolic form R implies the quantity not P and not Q. Next, consider the statement the sine function is a periodic function with period pi only if sine of pi equals 0 and sine of 0 equals 0. The component simple statements of this compound statement are P is sine of 0 equals 0, Q is sine of pi equals 0, and R is the sine function is a periodic function with period pi. The compound statement then has the form R only if Q and P. The symbolic form is then R implies Q and P. Next, consider the statement if the sine function is a periodic function with period pi, then sine of pi equals 0 is necessary for sine of 0 equals 0. We can use the same statement variables as in Part C. The compound statement then has the form if R, then Q is necessary for P. Since Q is necessary for P has symbolic form P implies Q, then the complete statement has symbolic form R implies the quantity P implies Q. Next, consider the statement either 42 is an odd integer and 6 is an even integer, or 7 is not an odd integer. This part is an additional example not in the notes. We can use the same statement variables as in Part A, so P, Q, and R are as shown. The compound statement then has the form either R and Q or not P. Now, using either or in this sentence groups the two parts of the disjunction. The first part will be R and Q, while the second part is not P. The compound statement then has symbolic form R and Q quantity or not P. And this concludes the video.